In this module, we will study about sources of organic compounds, differences between organic compounds and inorganic compounds, uses of organic compounds, bonding in organic compounds, representation of organic compounds, and molecular models.
Initially, all the carbon compounds were extracted from the natural materials obtained from the living organisms, that is, plants and animals, because they are found in the organs of plants and animals. These compounds obtained from the animal or plant kingdom were called the organic compounds. Until the early 19th century, it was believed that the organic compounds cannot be synthesized in the laboratory, but can only be isolated from the living beings. On the basis of this belief, in 1815, a Swedish chemist, Berzelius, proposed the vital force theory. According to the vital force theory, the organic compounds are produced only under the influence of some mysterious force existing in the living organisms. In 1828, Friedrich Wöhler, a German chemist, accidentally synthesized urea in his lab from ammonium cyanate. This synthesis clearly showed that no vital force was involved in the production of the organic compounds. Since then, a large number of organic compounds have been prepared in the laboratories and many more are being prepared daily. Now, with the downfall of the vital force theory, what should be the definition of the organic compounds? The compounds of carbon containing usually hydrogen and one more additional element such as oxygen, nitrogen, sulfur, halogens, phosphorus, etc. are known as the organic compounds. Though the oxides of carbon like carbon dioxide, carbon monoxide, bicarbonates, carbonates and carbides are also carbon compounds, but they are not treated as the organic compounds because their properties are quite different from those of the organic compounds. A separate branch of chemistry known as organic chemistry, which deals with the study of organic compounds. Now, some of the important sources of organic compounds are plants, animals, coal, petroleum, wood. We can also obtain organic compounds using synthetic methods. Let us discuss organic compounds like sugar, starch, cellulose, glucose, proteins, and many medicines are obtained from plants. Organic compounds like urea, proteins and fats are obtained from the animals. Coal tar is obtained by the destructive distillation of coal, which is used for the commercial production of many organic compounds like benzene, toluene, naphthalene, phenol, and pyridine. Crude oil found under Earth's crust is called petroleum. A large number of organic compounds like saturated and unsaturated hydrocarbons are derived from it. Some compounds like methyl alcohol, acetic acid, and acetone can be obtained by the destructive distillation of wood. These days, a large number of organic compounds are synthesized in the laboratories. Let's have a learning check. Predict the first organic compound that was synthesized in the lab. And your options are: the correct answer is option B, urea. Let us find the differences between organic and inorganic compounds. Organic compounds are the compounds of carbon except oxides of carbon, carbonates, and hydrogen carbonate salts. Whereas inorganic compounds are the compounds of elements other than carbon. Oxides of carbon, carbonates, and hydrogen carbonate salts are also classified as inorganic compounds. Organic compounds are generally insoluble in water, whereas inorganic compounds are generally soluble in water. Organic compounds are soluble in organic solvents, like alcohol, benzene, etc., whereas inorganic compounds are insoluble in organic solvents. Organic compounds generally have low melting and boiling points, whereas inorganic compounds generally have high melting and boiling points. Organic compounds are combustible, whereas inorganic compounds do not burn easily. Organic compounds are covalent compounds, whereas inorganic compounds are generally ionic compounds. Organic compounds generally have characteristic color and odor, whereas inorganic compounds are colorless and odorless. Organic compounds show the phenomenon of isomerism, whereas inorganic compounds do not show isomerism. Organic compounds usually undergo molecular reactions, which are slow, whereas inorganic compounds usually undergo ionic reactions, which are fast. We know that organic compounds are important to us. Let us discuss some of the uses of organic compounds. In our daily life, we deal with several organic compounds, such as clothes, soaps, detergents, plastic articles, and cosmetics. Fuels like petrol, diesel, kerosene, coal gas, CNG, LPG, etc. are mixtures of organic compounds. Organic compounds are also present in our food items. Fats, carbohydrates, proteins, vitamins are main constituents of our food, and all of them are made up of organic compounds. Medicines that we use to protect ourselves from diseases are made of organic compounds. We can simply put that there is hardly any walk of life where we do not use organic compounds. Now, we will learn bonding in organic compounds. Carbon has 4 electrons in its valence shell. It needs 4 more electrons to achieve the stable configuration of the nearest noble gas, neon. Carbon gets these 4 electrons by mutual sharing. Hence, it forms 4 covalent bonds, and the covalency of carbon is 4. We will start the discussion with the bonding in methane. In the methane molecule, carbon forms 4 single bonds with 4 monovalent hydrogen atoms to form the stable compound. In the ethane molecule, the 2 carbon atoms are connected by single covalent bond, while the remaining 3 valencies of each carbon are satisfied by hydrogen atoms. In ethene molecule, the 2 carbon atoms are connected by double bond, while the remaining 2 valencies of each carbon are satisfied by hydrogen atoms. In ethyne molecule, the 2 carbon atoms are connected by triple bond, while the remaining 1 valency of each carbon is satisfied by hydrogen atom. There are various ways to represent the structures of organic compounds, which include complete structural formula, condensed structural formula, and bond line structural formula. Complete structural formula is the detailed representation of the molecule showing all the atoms and the bonds through which they are linked. This structural formula focuses on the electrons involved in the bond formation. In complete structural formula, a single dash drawn between 2 atoms represents a single bond. A double dash represents a double bond, and a triple dash represents a triple bond. For example, complete structural formulas of ethane, methanol, ethyne, and ethene are as follows. The complete structural formulas are not convenient every time. Complete structural formulas can be condensed by omitting some or all of the dashes representing covalent bonds. The resulting expressions are called condensed structural formulas. The long condensed formula may be further simplified wherever possible. To understand this, let us consider the following examples. These formulas can be further abbreviated by indicating the number of identical groups by a subscript. So far, we were discussing complete and condensed structural formulas. Let us now learn bond line structural formula. It is a way of representing the structures in which carbon and hydrogen atoms are not shown, only bond lines are shown. The intersection of the lines and the end of the lines represent the carbon atoms. In bond line structural formula, it is assumed that the necessary number of hydrogen atoms is present to satisfy the tetravalency of the carbon atoms. The lines representing the carbon-carbon bonds are shown in a zigzag manner. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. To understand this, let us consider an example. Bond line structure of this compound is as follows. Here, terminals represent the methyl groups. Unsubstituted intersections represent the CH2 groups, and substituted intersection represents the CH group. Now it's time to check. Bond line structure of the given compound is as follows. Let's solve bond line structure of the given compound. What are molecular models? Molecular models are the physical means to have better visualization and perception of three-dimensional shapes of molecules. In the ball and stick model, the balls represent the atoms and sticks denote bonds. The molecular models of ethane, ethene, and ethyne are as follows. It's time to recall what we have learnt so far about organic compounds. The compounds of carbon containing usually hydrogen and one more additional element such as oxygen, nitrogen, sulfur, halogens, phosphorus, etc. are known as the organic compounds. The complete structure formula, condensed structural formula, and bond line structural formula are the ways to represent the structures of organic compounds. In this module, we will discuss homologous series, characteristics of homologous series, significance of homologous series, functional group, and some important functional groups. Is there any relation between the molecular formulae of the hydrocarbons shown? Let us observe the relation between the given molecular formulae. We can see that by adding the CH2 group in a first hydrocarbon, another hydrocarbon with a higher number of carbon atoms is obtained. Further, these compounds have similar structures with single covalent bonds and show similar chemical properties. Now these compounds can be grouped together in a family known as the homologous series. Let us learn more about the homologous series. A homologous series is a group of organic compounds having a similar structure and similar chemical properties, in which the successive compounds differ by a CH2 group. Each member of homologous series is called homologue. Methane is the first member of the homologous series of alkanes. On adding CH2 unit to the molecular formula of methane, we get the second member of the homologous series of alkanes and is called ethane. Successive members of this series are propane, butane, pentane, and hexane. The homologous series of alkenes is as follows. The homologous series of alkynes is as follows. Let's have a learning check. We know that the molecular formula of propene is C3H6. Can you predict the molecular formula of its next homologue? And your options are as follows. The correct answer is option B, C4H8. A homologous series is a group of organic compounds having similar structure and similar chemical properties in which the successive compounds differ by a CH2 group. So the hydrocarbon following C3H6 will be C4H8. The correct answer is. Each homologous series can be represented by a general formula. For example, the general formula of the homologous series of alkanes is CnH2n plus 2, where n is a positive integer. Solubility of successive members of the homologous series of organic compounds in organic solvents decreases with increase in molecular mass. All the members of a series show a regular gradation in the physical properties such as density, melting point, boiling point with increase in molecular mass. Boiling point of successive members of the homologous series increases gradually with increase in the number of carbon atoms. Boiling point. The members of any particular series have similar chemical properties. To understand this, let us consider an example. Methane reacts with chlorine to form methyl chloride and hydrochloric acid. Similarly, ethane reacts with chlorine to form ethyl chloride and hydrochloric acid. All the members of a homologous series can be prepared by using the same general method of preparation. For example, all alkanes can be prepared by heating sodium salts of the corresponding carboxylic acids with soda lime. Now, having learned the general characteristics of homologous series, let's try to answer this question. Arrange the following compounds in the order of increasing boiling point. You can choose from the following options. The correct answer is option C. Let's find the significance of homologous series. Knowledge of homologous series makes the study of organic compounds easier and systematic. By knowing the properties of the few members of a series, we can predict the properties of any member of that series. It also helps to predict the properties of even those members of the series that are yet to be prepared. Now, we will study about functional group. A friendly person shares a good bonding with the others. Friendly people keep interacting with their neighbors. Such people not only interact with humans, but also with their surroundings, such as animals or nature. Similarly, carbon is also a very friendly element. Till now, we have studied about the compounds of carbon and hydrogen. Carbon, being a friendly element, also forms bonds with the other elements such as oxygen, halogen, nitrogen, sulfur, phosphorus, etc. This other atom or a group of atoms present in a carbon compound is known as a functional group. A functional group is an atom or a group of atoms present in a carbon compound, which largely determines its properties. Functional group can replace one or more hydrogen atoms of a hydrocarbon chain, such that the valency of the carbon remains satisfied. This replacement forms another organic compound with different properties. Replacement of one hydrogen atom of ethane molecule with the hydroxyl group forms another organic compound called ethanol. Physical and chemical properties of ethane and ethanol are quite different. Hence, we can conclude that the functional group largely decides the properties of the new compound. Functional group is mainly responsible for the chemical properties or reactivity of organic compounds. Physical properties of organic compound are largely determined by the alkyl group. Gradual changes in the physical properties of organic compounds are observed with increase in the number of carbon atoms. What are the characteristics of a functional group? Let's find out. The chemical properties of the compounds containing the same functional group are similar. The physical and chemical properties of the compounds of different functional groups are different. There exists a homologous series of compounds containing a particular type of functional group. We will now be discussing some important functional groups present in organic compounds. The structures of some of the important functional groups are as follows. The free valency of the functional group is shown by a single dash. The functional group gets attached to the carbon chain through this free valency by replacing the hydrogen atom. Replacement of one hydrogen atom of methane molecule with the halo group to form haloalkane is shown here. Replacement of one hydrogen atom of methane molecule with the alcoholic group to form an alcohol molecule is as follows. Here you can see the replacement of one hydrogen atom of methane molecule with the aldehydic group to form a molecule of aldehyde. Let us see how a ketone is formed. Replacement of one hydrogen atom of methane molecule with the carboxyl group to form a carboxylic acid molecule is shown here. When an oxygen atom intercepts a carbon chain, such a functional group is known as alkoxy group. The compounds that contain the alkoxy group are called ethers. Now the correct answer is option A. Now, let's solve the correct. We know that the organic compounds having similar functional groups can be arranged in the form of a family known as the homologous series, in which the successive members differ by CH2 unit. Now, can you write the homologous series of alcohols? The homologous series of alcohols can be represented by the general formula CnH2n plus 1 OH. The first four members of this series are as follows. All the members of this group possess the same functional group. Let's summarize what we have learned so far about homologous series and functional groups. Homologous series is a family of organic compounds having the same functional group, and the successive members of this series differ by a CH2 unit. All members of a homologous series can be represented by a general formula. All the members of a homologous series show a regular gradation in the physical properties, but they show similar chemical properties. A functional group is an atom or a group of atoms present in a molecule, which largely determines its chemical properties. Physical properties of organic compound are largely determined by the alkyl group present in it. There exists a homologous series of compounds containing a particular type of functional group.